In this video, I'm going to go over two proof techniques. We're going to talk about direct proof, not we, I am. I'm going to talk about direct proofs and indirect proofs, show you a couple of examples, and then we'll be able to play in class on Wednesday, practicing some of these. The first proof technique is called the direct proof, and we're going to look at the direct proof for something of the form P implies Q. Almost everything we will prove not everything, almost everything we prove will be of the form P implies Q. To show that P implies Q is a true statement, remember if P is false, the statement is true. So we don't need to worry about that. We're going to assume that P is true and see if we can work our way down to Q. So the form for a direct proof is assume P. Whatever the P is, assume P is true. Then that'll get you somewhere, and that'll get you somewhere, and you go yada, yada, yada. Eventually you'll hit Q. When you get to Q, you have proven that P implies Q. So you start with P, yada, yada, yada. That is a proof for P implies Q. Let me look at an example. If M is odd, then M squared is odd. Before we prove this, we're going to need some definitions, because to prove something is odd, we need to know the definition of odd. And we need to know the definition of even, because that's the opposite of odd. So let's start with that. N is even if and only if there is an integer such that n is equal to 2 times k. Even, that's how we define even. So if we ever want to show something is even, we want to show that it's equal to 2 times crap, where crap is some integer. N is odd if and only if there's some k in the integers, where n is equal to 2k plus 1. So we know it's odd if we can write it as 2 times something, where we know that something is an integer, plus 1. Okay, with this in mind, let's go back and look at this proof. M is odd, then M squared is odd. So I'm going to start with assume M is odd. What does that tell me? It tells me M is equal to 2k plus 1 for some k in the integers. I want to prove that M squared is odd, so I need to play with M squared. What is M squared? Well, since M is equal to 2k plus 1, M squared is equal to 2k plus 1 quantity squared. Let's crank that out. 4k squared plus 4k plus 1, which if I suck out the 2 from those first two terms, I have 2 times crap plus 1, which is what I need. Therefore, since 2k squared plus 2k is an integer, I know that m squared is odd. And the last step of your proof is the ta-da. Therefore, that's what those three little dots mean, is therefore. Therefore, if m is odd, then m squared is odd. If x is even and y is odd, then x plus y is odd. I start with assume x is even and y is odd. And where am I going? I want to say that x plus y is odd. I get to that by getting x plus y is odd, which means I need to be able to say x plus y is equal to 2 times crap plus 1. Okay, let's go back to the top. I've got x is even and y is odd. What does that mean? Well, that means x is equal to 2 times m and y is equal to 2 times n plus 1 for some integers m and n. Notice I use two different integers because I don't think x and y, there's no reason for them to be related. If I said 2m and then 2m plus 1, that means x and y are right next to each other. That I don't know, and that's an assumption I can't make. I want to be two different, totally different numbers. So one is 2m, the other one is 2n plus 1. Now let's add them. X plus y is 2m plus 2n plus 1. Well, I have it. There's 2m plus 2n. I suck out the 2, and I have what I want. 2 times m plus n plus 1. That means that x plus y is odd. Ta-da, I'm done. Let me give you a couple more definitions. Well, at least one more definition. We say a divides b if and only if there is some k in the integer where b is equal to a times k. A divides B. A goes into B. The notation for this is A with a vertical bar, B. Now I know what you're going to do. You're going to start making that bar slanty. And then before you know it, that A's on top. And this is totally wrong. It's the B that's on top. So we do not want to see that. Okay, I want to prove that for all integers A, B, and C, A divides B and B divides C implies A divides C. I read that in English, though you may be looking at the notation going, what? In English, for all integers, if A divides B and B divides C, then A divides C. So let's prove this. Restate what I'm proving. And you should always write down what you're proving. I'm proving that for all a, b, c element of the integers, a divides b and b divides c implies a divides c. Assume what you're given. Assume a divides b and b divides c. Now what does that mean? That means that b is equal to a times m and c is equal to b times n for some integers m and n. Again, notice I use two different integers. Where am I going with this? Well, my bottom line wants to be, ta-da, I've proven that if a divides b and b divides c, then a divides c. And I get to that point if I can get c equal to a times something. So let's look what we've got. We've got b is equal to a times m, and c is equal to b times n. Well, I want c is equal to something, so I'm going to start with that. And here is a b, which I know b is a times m. I'm going to substitute that into here and see what that gives me. I get c is equal to a times m times n. Well, if I just move those little parentheses around, I have exactly what I want. I have a times crap, where crap is m times n. That is what I want. So I now have c is equal to a times crap, m times n, which means a divides b. Ta-da, the proof is done. The other kind of proof I want to look at is an indirect proof, also known as proof by contradiction. If I want to prove a statement S, I start with assuming that it's false. Assume not S. And then yada, 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 I get to something that's obviously false, like pigs fly, and that means my original statement had to be true. Let's try an example. There are infinitely many primes. Well, suppose not. Suppose there are finitely many primes. If there are finitely many primes, I can list them. The first one, the second one, yada, yada, yada. I like that word, yada, yada, yada. It's very mathematical. I can list them. I don't know how many there are, so I'm going to assume there are n of them, where n is some integer. So I will say, let p1, p2, dot, 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 pn be the set of all primes. Now the next step is going to seem like I pulled it out of my ass, and I did. What you are seeing is the finished product. You haven't seen the piles of paper that I've scrapped on and made notes on and made it nice and pretty. It's like when you write an essay. People don't see all the stuff you did before to get the nice pretty essay with the English. They don't see your rough drafts. They just see the final one. So this is the final one. So what am I going to do with this? I'm going to say let m equal p1 times p2 times p3 times dot, 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 up to pn plus 1. Now since m is the product of all the primes plus 1, I know that m has to be greater than p sub I for all of them, which means m is not in the set, which means m is not prime. If m is not prime, one of the primes has to divide it. I don't know which one. Some of them. It is convenient for me to pick one out because I don't know how many are in here, but I could say, well, suppose P1 does it and then prove it. Well, suppose P2 does it. Da, da, da. The proofs are going to be the same no matter which P I choose. So for convenience, I will say, without loss of generality, suppose that prime is P1. P1 divides M, which means there's some K where M is equal to P1 times K. Now I need to work toward a contradiction. M is equal to this gross thing up here, so let's fill it in. So I have P1 times P2, yada, 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 plus 1 is equal to P1 times K. I'm going to do some algebraic manipulation. I'm going to pull this P1 to Pn product and bring it over to the other side. So I now have 1 equals P1K minus P1 dot, dot, dot. Both of the terms on the right have P1s, so I can factor it out. Now, remember the definition of divides by, or something divides something else. I have P1 times a whole bunch of crap is equal to 1, which means P1 divides 1. But that would mean it's equal to 1, and 1 is not a prime number. All the primes have to be bigger than 1. This is the contradiction. My cows are flying. I know the original statement is true. There are infinitely many primes. If we want to do an indirect proof of P implies Q, we want to assume that it's false. Just like we assumed the S was false before, we're going to prove that P implies Q is false. To do that, we assume P and not Q. And that'll lead us to something, and eventually we'll get to pigs flying. I keep saying pigs, I did cows flying. That will lead us to cows flying. So that means the original statement is true. And let's look at an example of this. If n is irrational, then 5n is irrational. Suppose not. Suppose n is irrational and 5n is rational. So what am I proving here? What do I know? So if I assume n is irrational and 5n is rational, what can I say? Well, I know that 5n has to equal a over b for some a and b in the integers. But that means 5 times b is an integer, because b is an integer, 5 is an integer, 5 times b is an integer. Why do I care? That means a over 5b is rational, but that's n. That means n is rational. Contradiction. Therefore, if n is irrational, then 5n is also irrational. So those are proofs I want to do for you. We will do a lot more in class, don't worry. I'm trying to stick with mathematics. It's not too funky. And I think that's a good place to stop.